Hello everyone, today we're talking about solution sets of homogeneous systems. This is material from 1.5. So maybe just to start off, what the goal is for today is to provide a, let's call it geometric description of the general solution, let's say for certain systems. So we've already seen what it means to give the general solution, right? We want to look for pivots and free variables, and we want to describe the pivot variables in terms of the free. Today we're actually going to use vectors to give a geometric description. So let me start with a definition here. A homogeneous system, so this is in the title of this lecture. So a homogeneous system is one of the form. So it's a system of the form, I'm going to use the matrix equation description. So this is AX equals 0, let's say where A is an m by n matrix and 0 is the 0 vector, right? So this will be 0, 0. This will be in Rm for this to make sense. So the point is that the homogeneous system, you know, if I had to say this in words, this has zeros on the right-hand side. So everything, you know, if you think about this in terms of equations, every equation has just equals 0. Whatever the first equation is, it equals 0, same for the second, etc. Now, what's interesting about homogeneous systems, or why are they kind of special, is that, note, important fact here is that a homogeneous system always is consistent. It always has a certain solution. The solution, right? So think about this if you want in terms of equations. What's a choice for the variables x1, x2 up through xn that always works? Well, if the right-hand side's equal to 0, then I can always plug in just everything equals 0, right? So x equals the 0 vector. Notice that this is the vector in Rn now because I have n variables. Okay? Yeah, so this is an important observation. I can always plug in all variables equal to 0. Since the right-hand side of the equations are all equal to 0, then it'll always work. This is called the trivial solution. I mean, because it's trivial in the sense that it's always there, it's 0. And so another important maybe fact that we can now kind of draw from this, so we know this thing's always consistent, so now the question is, does it have one or infinitely many solutions? And we know that AX equals 0 then has a non-trivial solution, right, another solution. How do I detect that? Well, as usual, this is going to be detected by, you know, your echelon form. So, as you guys know, this will happen if and only if you have a free variable. Okay, so if we know this thing is consistent, then we just have to, you know, look for free variables. If there is a free variable, it's got an infinite number of solutions. In particular, it has, so maybe I can just say, in which case, you know, not only does it have a non-trivial solution, it actually has infinitely many non-trivial solutions. Infinitely many solutions. Okay, so I think I'll do this with an example. But those are the kind of main, points to realize for homogeneous systems. Let's do an example now. So let's consider the system. Well, let me write this as a system. 3, 5, minus 4, minus 3, minus 2, 4, 6, 1, minus 8. And this is homogeneous. I'm going to have zeros on the right-hand side. So one more time, this is the augmented matrix of a system. So, you know, really this is like 3x1 plus 5x2 minus 4x3 equals 0, ... right? That's the underlying system, but I'm slowly I keep threatening you with this, but I'll slowly stop writing the actual equations. I just want the augmented matrix. Okay, so let's reduce this guy. Press my kind of magic row reduction button. And if I go to echelon, this thing looks like, turns out it's 0, 3. I mean, this is one of the echelon forms. I get to this guy. And now, what do I see here? Well, I see pivots in columns 1 and column 2. So we know that this thing is consistent. It always will be consistent. But we see here that free variable x3, which implies that you have infinitely many solutions. Okay? Let me just comment that I skipped the row reduction here, but notice that one thing to notice for homogeneous systems is that when I do a row reduction, right, so maybe I would add row 1 to row 2 here, notice that if there's zeros in the last column, there always will be 0, right? They'll never change. So often when you're dealing with homogeneous systems, you actually don't even care about this right-hand side column. You just look at the coefficient matrix, because it'll always be 0 on the right-hand side. Anyway, so let me keep going further because I want to describe those solutions. So let's further reduce to, this was the echelon form here. This was echelon. Let's further reduce to reduce for echelon. This will look like, well, 0, 0, 0. This will be, of course, 0, 1, 0. And this will be 1, 0, minus 4/3, 0. Okay? This is now reduced echelon. And what do I see here? So the usual thing, right? Well, I know my pivots are here. So this means that x3 is free. What is x2? Well, actually, that second equation is just saying that x2 equals 0. And this equation is saying that x1 equals 0, right, plus 4/3 x3. Right, if you solve this first equation for x1, you get x1 equals 0, and you bring that minus 4/3 x3 to the other side, you get this. Okay, so this is old news. This is what we've seen before. Here's the new ideas. We want to describe the solution. So now we want to describe the solutions as vectors. Okay, so what do I mean by that? Well, so we know a solution for this guy will be of the form, it's x where I have 3 variables. So what I'm doing is I'm putting those 3 variables into a vector, right? I know there's 3 variables here, so a solution will consist of 3 numbers. I put them in a vector. And what I do now is I just replace, here's my information that I now know. I just replace everything here with what I see. So x1 looks like 4/3 x3, right? I'm just replacing x1 with what it is. x2 is 0, and x3 is free. So what I'm going to do is I'm going to say, well, x3 can be whatever it is. I'm just going to call it x3. Okay, so whenever you see a free variable, you just, replace it with itself, if you like, okay? And so what I've done now is I've taken the information from what the solution set is telling me, but I'm putting it into a vector form. Now I want to go one step further. I want to actually factor out an x3 here, because I notice everything is multiplied by x3. I can take out the x3, and I get 4/3, 0, 1. Okay? Okay, and so this is now what I call the parametric vector form. So this is called the parametric vector form of the general solution of the general solution. And what is this saying geometrically? So I promised a geometric description here. Well, if you like, what's happening here is this is telling me that any multiple of this vector 4/3, 0, 1 is a solution. So let me just give you kind of a cartoon picture maybe. If I sit in 3 dimensions, this is x1, x2, x3. Let me just draw this vector. So this might not be quite right, but let me just think of this as, this is 4/3, 0, 1. So I don't know if that's quite right, but it looks like something. And what I'm saying is that not only is that a solution, not only is this a solution, but any multiple of it. So I can take, twice it. I can take minus a half of it. I can take minus 2 of it, or whatever that is. So anything along this line, this is the solution set now. So notice in particular, 0 is allowed, right? Because I can take 0 times, so the origin, which is 0, 0, 0, that's allowed, that's a solution. But anything along this line is also a solution. In fact, all solutions sit on this line. Okay, so you got a nice geometric description of all possible solutions. You can check if you put in, if you multiply this by 3, you'll get 403. That will be a solution to the given system. You can check. But again, the idea here is we've got a nice picture to draw. Let me do one more example. Let's consider this system. I'll put this in quotes. It's going to be just one equation. So this is a homogeneous, this is, a 1 by 3 homogeneous system. There's only one equation, 3 unknowns. That's okay. You can have just one. Let me consider the augmented matrix. Well, maybe it looks kind of funny, but it's 10 minus 3 minus 2, 0. That's already in echelon form, right? Because here's my pivot. Let me reduce this to reduced echelon. I'll multiply everything by 1/10, and I get this. This is now reduced echelon. Okay, and so here's my one pivot. What is this telling me? Well, it's telling me that, x3 is free, x2 is free, right? There's no pivots in those columns. And what's x1? Well, let me solve for it. This is just saying that x1 minus 3/10, x2 minus 2/10, x3 equals 0. In other words, x1 equals 3/10 x2 plus 2/10 x3. Okay, well, let me do that same thing in vector form. What I get is that x, my solutions, are going to look like x1, x2, x3. What I now know is that x1 is 3/10 x2 plus 2/10 x3. x2 is free, so I just put in x2. x3 is free, I just put in x3. And now what I want to do is, again, break this up as I factor out the x2 and x3 as I did before. But notice that I've got x2 and x3 in there. So what I'm going to do is just break this up into kind of the x2 parts and the x3 parts. So if I look at this vector, how much x2 is in the first coordinate? Well, there's a 3/10. Right, there's a 3/10 x2. How much x2 is in the second coordinate? There's 1 x2. How much x2 is in the third coordinate? None. Similarly, for x3, I've got a 2/10 in the first coordinate. I've got no x3 in the second coordinate and 1 here. Okay? So this is the vector parametric description. I'm going to use both of those words because I think the book kind of moves back and forth. This is the description of the solution set. Now, can I draw a picture of this? Well, again, I'll draw kind of a cartoon here. We're sitting in 3 dimensions again. Now I've got 2 vectors. Let's call this, let's say this is 3/10, 1, 0, and let's say this is 2/10, 0, 1. Again, these are not going to be accurate pictures. I'm just trying to give you a cartoon sketch. But what it's saying now is the description, the description of the solution set that I'm getting is I can take any linear combination of these two, right? This should look familiar. It's something times this vector plus another number times the other vector. So you've seen this before. This is the span of these two vectors. And what is that? Well, these vectors are not parallel, so the span, as we've seen before, will be a plane. So this will be a plane given by the span of, well, those two vectors, two given vectors. Okay, and so again, you have this nice picture. You have a plane's worth of solutions. So like any vector in this plane, would be a solution. You got sort of a 2-dimensional solution set here, and we'll make that more precise later. But again, the solution set is this, this object. It's given by this parametric description. Let me just finish by kind of conclusion here, or maybe punchline, is that the solution set to a homogeneous system let's say AX equals 0, right? That's a homogeneous system, is always given by the span, let me say it this way, span of a bunch of vectors, v1, v2 through v, let's say, p, where, so what do we have here? So in this example, I had 2 vectors. The span of these 2 vectors gave me the solution set. Notice that there were 2 free variables. Right, so if you go back to our first example, the span was just, of 1 vector here, this 4/3, 0, 1, and that corresponded to having 1 free variable in that first example. So what you're going to have here is you're going to have 1 vector for each free variable. Okay, so that's kind of a nice thing to notice. I should also say that if no free variables exist, then the solution set is just the trivial solution. So I'll write that as like the set containing the zero vector. What I mean by is that it's only the trivial solution. Okay? So that's kind of an observation we're making. We're going to use that. This is for homogeneous systems. Next time we'll talk about what happens for general systems, and we'll see you next time.